Okay, so let's start streaming here. Oh wait, presenter. Where is that? Here we go. Usually I have this set up before I start. Sorry. Well, I guess you're used to this by now. My screwing things up. Okay, so what we're gonna do this go round is So here's the same problem we've been solving for the past couple of videos. And now you can solve them in Nastran. In MATLAB. You can solve them by hand. I didn't do a complete MATLAB video. I probably should do another one, but I think you get the idea, and I think they'll cover some more in the class. But let's take this problem and let's solve it in Nastran, okay? And we will do both one Nastran input file solving the two cases, okay? All right, so what we're going to do, I'll do this without going through all the details of Nastran. When I used a different book that did bar elements first, and we would start off with C rod elements, basically. But this text starts off with springs, so we'll start off with the Nastran spring element. The element that we're going to use to do a spring is going to be a CELAS2 element. There's actually 4 CELAS elements. They're all springs. They have some subtle differences. Well, they work for different types of grid points, and some of them use a separate property card. For our purposes, CELAS2 will probably be the easiest. This is going to be a spring element. And to define the nodes, we're going to use the grid card. Those are going to be nodes. And to define the forces, well, this one's pretty easy to remember. That defines the forces. And lastly, we will use an SPC card. To define the constraints. It's called the displacement boundary conditions. All right. Okay. And do I have it going on here? Let's see. There we go. All right. Not this one. This is here we go. This is the go to the front page, the Nastran Linear Static Analysis User's Guide, which is put on Blackboard for this class. This is really a useful document. It's laid out very well. You can see over here the table of contents. It breaks it down by scalar points, elements, materials, loads, so on and so forth. So, for example, let's say you wanted to look at the format to do a grid point. So you just click on grid point, and this gives you the actual format to define a grid point. And we're going to talk a little bit about this format. It might be a little bit different than what you're used to, but this is based on the very, very old days when you used to actually have little punch cards to submit your jobs on a computer. And you have these sort of 10 fields, and we'll talk about how you write an input file for Nastran. Actually, most commercial finite element programs still use some variation of this format, okay? But get this file, download it for reference. Like I said, it'll show the format and describe everything you need to know about all the fields for a grid point. I will not go over all those. Likewise, if you want to look at scalar elements, it'll tell you all about the CELAS 1, 2, 3, and 4, give you all that stuff. If you want to look at the forces, that's under the static loads. Probably it's this one. Force. And last one, SPCs will be under constraints. Single point constraint, that's what it stands for, okay? Constraint at a single point. And again, gives you all the information you need to know. And I will not go over all those fields right now because it'll take too long, and I gotta go home a little bit anyway, okay? All right. Okay. So fine. This is our problem. Okay. Let's talk about Nastran, and actually all finite element programs. Although a lot of times we use a graphical preprocessor, and we will use those in this class, ultimately the graphical preprocessor writes out what we call an input file, which it submits to the solver. That input file is actually a text file, or sometimes we call it an ASCII file. And you actually don't need the preprocessor. You can write those files directly. And for a good portion of this class, that is what you'll be doing, because the problems are relatively simple. All right? So I typically start off with a sort of a template, okay? And that's what I've done here, all right? We've distributed something similar to this in Blackboard for the class, but this is a good one to start with, and I've kind of increased the font size so hopefully you can read it, all right? This is just a text file, okay? I use this program called Notepad++. It's really good. Actually, I have a little predefined formatting for Nastran files, but also works for different types of programming languages. Do not use Word. Do not use a word processor because, first of all, they don't generate text files. They generate some sort of binary file. And they will stick, even if you use something like WordPad, it'll stick weird symbols in there, which will screw up your ability to run. So you can use Notepad, but I would recommend actually getting Notepad++. It's free and it's fine. If you use a Mac, a good one is Wrangler, I think. Right? I think that's a good one, and it's also free. Okay. So this is just to save me typing all this stuff in. Okay. All right. Any line that has a $sign, that what goes to the right of that is a comment. So all this green stuff here, whoops, is comment. That means that Nastran does not read any of this stuff. It doesn't read any of this. It doesn't read, it keeps collapsing, doesn't read any of this, okay? But I have these here to help me write these files by hand, okay? So the first thing I always like to do is, here's a little cartoon of the problem, okay? This is the problem that we've been using, right? That one, there it is, right? You don't have to do that, okay? So be it. And I define the two cases. And I put also the units, because for finite elements, there really are no units, okay? So it's useful to sometimes put the units, at least somewhere, as a note. And then my email address, for whatever reason that is. Okay. All right. Now, let's talk about this a little bit. I'll get back to some of that other stuff, but let's just talk about the main bit describing these parameters. Like, for example, let's look at grid. I talked about grid. We need to define some nodes. So here you can see is the Nastran documentation for what's in a grid. And you can see it has these 10 fields. The first one has this card grid, and the second one is an ID number. It tells you what that is. That's actually whether it's node 1, 2, 3, or 4. And then field 3 we won't use, but then the X, Y, and Z coordinates are in field 4, 5, and 6 respectively, okay? These have a fixed length. They have to be 8 spaces each. Some fields take integers, some fields take floats, like a number, and you have to put a decimal place in a float. And you have to not put any decimal places in an integer field, otherwise you will get an error, okay? All right, and where the numbers go in those fields doesn't matter. So I use this little thing here. This is my cheat. This shows me that here's the first character, second, third, fourth, fifth, sixth, seventh, eighth. That's field 1. Now for field 2, 1, 2, 3, 4, 5, 6, 7, 8. Field 2, field 3, 4, 5, 6, 7, 8, 9, 10, so on. So I always use this when I want to do a new card. I just copy it over, and then, so for example, here I have to do a grid. So what I did was kind of took the names of the fields here and just rewrote them here so I can remember when I type stuff in, okay? Okay. All right, there's 3 main sections here. One is this executive section, which tells Nastran what solvers to use. We'll always be using Solver 101, so you don't have to worry about that. Just type Solver 101. Then you have another section, which is a load case section. We'll talk about that. That's how we're going to define the 2 cases. And then the last section, which is probably the section we'll do most stuff with, is this bulk section, okay? And this is where we define nodes, elements, material properties, forces, constraints, all that sort of stuff, okay? Now this line here, you don't really need, but I suggest putting it in because for us this will also generate a XDB file that we can then look at in HyperView, which is a nice post-processing program, okay? All right, and maybe we'll do that in another video or something. Okay, so let's go back to our problem. Let's think about what we need to define. Well, we need to define the nodes, or in this case, the grids. There's going to be 4 of those, 1, 2, 3, and 4. Then we have to define the elements that connect it, element 1, element 2, and element 3. Then we have to define the force, and also we have to define the boundary conditions, and we have 2 cases of those. So we have to somehow say these boundary conditions are for case 1, and these boundary conditions are for case 2. We'll talk about that, okay? So let's first just set up the mesh, if you will, right? The nodes and then the elements, okay? All right. Now, once you get down past this begin bulk section, it doesn't matter the order you do stuff, but it's probably reasonable to do nodes, materials, elements, and then boundary conditions, okay? All right. So we have 4 nodes to define, okay? The second field is a node ID, and then we have the X, Y, and Z coordinates, okay? Now, actually for spring elements, it really doesn't matter what you use for the nodal coordinates. The stiffness of the element is completely defined by the K of the element. So whether an element is this long, or in any orientation, the K is going to be the same regardless of where the nodes are. But just to make it look good and not to freak out students too much, I'll actually put coordinates in here. So this will be x equal to 0, x equal to 1, x equal to 2, and then we'll call this y equals 0 and plus or minus minus 1, okay? So for whatever it's worth. So for the first node, right? And you have to use spaces, not tabs, so I'm using spaces. The ID is 1, and it's going to be at 0, and then we'll call it at -1. Whoops. And then the Z value is going to be 0, all right? So you notice I put a decimal place in here. You have to do that because these are floating values. You can call it 0.0, that works as well. But usually we just to save space, I do 0 plus because 10 is actually not a big field. All right, that's the first node. And then I will just cut and paste and do the other nodes. Node 2, node 3, and node 4. Node 2 is at the same x value but has a y value of 1. Node 2 is at points 1 and 2 respectively in x, and then 0 in y. And again, really, it doesn't affect the results, and if you don't believe me, you can either rerun this with different values and you'll see you get the same results, or more importantly, you probably should review the theory of the spring element and see why the coordinates don't come into the stiffness matrix at all, okay? They will for bar elements and beam elements, all right? Okay, so we have the 4 nodes defined. Now let's do the element. So when you look at the element card, we're going to use a CLAS2. Again, you can go back to the linear static reference manual under scalar elements and read all about the different CLAS elements, but we're going to use this formulation, okay? The first field is a unique element ID number, so we need to do that. The second field is the K value for the spring. Then the third field is what's the first node that spring's connected to. And then we have this component, which I'll explain in a second, for the first node. And now we have the second grid point that the spring element's connected to. So for example, our first element connects grids 1 to 3. So you would have a 1 here and a 3 here. All right? Let me fill it. So the first element, here we have a 1. The K value for the first element is 50, and it's a floating number, so I have to do 50 point, right? And it's going to connect node 1 to node 3, all right? And I should have mentioned this too. you have to make sure these values are somewhere in this field. For example, if I do this, this will give me an error because it'll read the K value as, like for example, if I do this, it'll say the K value is 50 an integer, which gives you a problem, and it'll read as the value for the first node a float, 0.1, because this decimal point is actually in the fourth field, the G1 field, okay? So you have to be really careful to make sure that they are in their fields. They can be centered and stuff if you want to. I usually put them to the right, just out of habit, right? And that's why this delineator is actually a greater than sign, because it means like this, what I mean by that is like this space here is actually in that field, okay? For whatever it's worth, okay? So that means, well, I'll do one in a second, right? So, okay, so here's the nodes that it connects. Now, what about these C1 and C2? Well, these are springs, so you can actually connect a spring between like the X degree of freedom of one node to the Y degree of freedom of another node, all right? So we're just using X degrees of freedom. So that's going to be a 1 here. Whoops, what happened there? And then a 1 here. Okay? So this is saying we have a 50-pound spring that connects the X degree of freedom of node 1 to the X degree of freedom of node 3. All right? Now we can go through and define the other two C-last elements. They need to have unique IDs, 2 and 3. The second element has a spring stiffness of 100, and the third has a spring stiffness of 60, right? The second one connects node 2 to node 3, the X degree of freedom for node 2 and to the X degree of freedom of node 3, and the third element connects the X degree of freedom of node 3, X degree of freedom of node 3, to the X degree of freedom of node 4. All right. So now we've got all our spring elements. All right. Now we have to fix the nodes. All right. Now here's a little trick actually, and this is a problem with there's scalar points which sometimes I use, but I think in this class we'll use grids. But we have to do one other little step. The grid point, you know, this is Nastran, so it's actually by default it's always assuming you have a 3-dimensional model. So each node has 6 degrees of freedom, 3 displacements and 3 rotations, right? And they're all active, all right? So we want a very simple problem. We want a problem where the nodes just move in X. So I could actually put SPC constraints on like all the other degrees of freedom. You could do that. But there's actually a little trick that allows us to do it a little more simply, okay? So this, for each one of these grid points, there's this PSPC. It stands for permanent SPC. So you can put here degrees of freedom and it'll fix them. So for all these nodes, we actually want only the X degree of freedom active. So if I put down here, whoops, not that. If I go into this field and I do 2, 3, 4, 5, 6, that means that translation of the Y and the Z are 0, as well as the rotations around the X, Y, and Z. The only active degree of freedom is the X translation. So I'm going to do that for all of these guys, just to make my life easier. If you don't do it, you will get an error because you have rigid body motions that are allowed in the Y and the Z directions, as well as those rotations, okay? Actually, it'll condense out the rotations, but in general, it's a good practice just to constrain all those. So for this chapter, we're going to be doing everything just in moving in X. So for the grid points, put 2, 3, 4, 5 here, okay? That'll stop the nodes from moving in Y or Z or rotating around X, Y, or Z, right? Something like that, whatever. All right, so we got our spring elements, we got our nodes, that's great. Now we have to talk about our boundary conditions, our SPCs, okay? So here's the SPC card. Move this up just a little bit, right? Again, it has a similar thing. It has a grid and a component, all right? So our first, let's do node 1, okay? We'll do node 1. So node 1 is, and we'll just consider the first case for now. So node 1, it's grid point 1. We're constraining the x component, and it's going to have a value of 0. All right? So that's what's going on here. This is the grid, this is the component, and this is the value you set. You can leave this blank, it's going to assume it's 0. All right? And let's do the same thing for the second node. Second node, fixed, displacement 0. But we also have the other set where we're going to put a motion on the second node. For example, in one case, we're going to fix it, and in another case, we're going to move it, right? So we're going to have two what we call load cases. And we need some way of differentiating the boundary conditions from one load case from another load case. They're still going to use the same nodes and elements, right? So how do we do that? Well, that's what this first field here is for. This is a load set ID. So you can put an integer here to basically group the boundary conditions. So we have two cases. Let's call the first case 1. And you can see here, these two boundary conditions are grouped together. We're going to use them in one load case, okay? These are load case 1. You can call it whatever number you want. You can call it 99. It doesn't really matter. And then we will do another one here. I'll call it load case 2. So you can see now I have two SPCs for load case 1, where both nodes are fixed, and two SPCs for the second load case. Node 1 is fixed and node 2 moves. Okay? All right. So how do we tell it to do that? Well, now we go back up to the top. There's this load case situation here, right? So you can see I have a subcase 1, and that, I'm going to just copy and paste this, and I'm also going to have a subcase 2, all right? All right. The title is the name of the problem. You can call it what you want to call it. Simple spring problem. Whatever you want to call it. You can call it Fred. Doesn't matter. All right. Let's not worry about all these for now. I'll explain those in a second. But let's look at SPC and load. This is where you identify the set IDs that are going to be used for this solution. Okay, so for this first subcase, which SPC set do we want to use? Well, it's these ones with set ID 1. So whatever number you have in this second field has to go here. So we're going to use 1 for load, and likewise for the second case, we're going to use set 2. All right. All right. Now, let's do the forces. So that's so it's just like an ID, or like if you want to think of it like a storage device, right? It kind of groups them together, right? All right. Now we have to do the force. So let's define the force card. This is going to be a set ID. You can call it 1 or 2, but actually let's call it 3, and I'll explain why in a second. The force is applied to grid point 4. Don't worry about the CID for now. The rest of the force is defined in the next 4 fields. So the F field, which is field 2, 3, 4, 5, field 5, is the magnitude of the force. So that for us is going to be 200. It's a float, so I have a decimal. But you have to say which direction is that vector act in. So N1, 2, and 3 are the X, Y, and Z components of a unit vector. Make it a unit vector where that force acts in. So for us, it's going to be 1, 0, 0, and those are all, floats, and so we have to put the decimal place after all of them, right? Okay. Believe it or not, this is legitimate. This actually means the same thing. So this actually means 0 point in this field and then 0 point in this field, okay? So you don't need any space between the fields. That's the nice thing. Saves a couple of spaces. but the bad side of it is a little difficult to read. Okay, so be careful about that. You'll definitely make mistakes on that to begin with. Okay, so here's my force vector, 200 pounds in the x direction on node 3, and I called it set ID 4. I'm sorry, set ID 3. Okay, now we want to use this force both in load case 1 and load case 2. So I'm going to go up here, and you can see we have load. So I'm going to put the 3 here. Okay, that means we're using this force, or all the forces in set ID 3. There could be multiple forces, and we're applying those in load case 1 as well as load case 2. And you'll get results for both these cases. Now, you could have multiple forces, multiple SPCs. A lot of times you could have 10, 100 different load cases for a problem. Okay, so it just makes it a little bit easier. All right. It actually runs faster as well because you only have to factorize the stiffness matrix once and then solve it for all the boundary conditions. So if you have like 100 load cases, you only have to basically solve KD equals F, ostensibly do the work for it once, and then to solve for each load case, it's much less work. So it can be significantly faster if you have lots of load steps or load cases. Okay. All right. Well, that's pretty much it. Then we got this end of data. That's the end of file. So this thing is ready to go. All right. So we said we're using the linear elastic solver. We've given it a title. We've defined 2 load cases with different SPCs, but the same forces for each load case. And now we have this bulk section where we define the grid points or the nodes. We constrain, in this particular problem, we constrain everything except the X degree of freedom up here with this permanent SPC card in the grid. Then we have our elements, our other constraints, like our boundary condition constraints, and our forces. And that should be it. So now I'm going to save this text file, and now we're going to run it. And hopefully, well, if we get some errors, we'll debug it, but this should work. Now, the Nastran program itself, when you install it, is pretty boring. It doesn't do anything except bring up a file manager looking thing, right? So this is what it is, all right? Now let me also open up, where did I save this? Okay, this is on my desktop. So let's go to my desktop and you'll see my input files here. And while that's going on, let's, I should have put it in a subdirectory, but let me quickly put it in a subdirectory just to, I'll show you why so you can see how it executes. So this is good. I'm going to create a subdirectory off of my desktop. I'll call it Spring. Where'd it go? I don't know where it went. I have multiple screens, so that's why you can't see everything. And let me move that Spring BDF into it. Oh, what the heck? I didn't want to do that. This is so unprofessional, right? Well, whatever. Where'd it go? Spring. Can't even see what I'm doing, can you? Because I'm on a rather. Need to play like the Jeopardy music when we're doing this. Paste. All right. So you'll see why I did this. So I have a directory that's just got that file for now. We can open it up and edit it. That's fine. The font's really small. Let's make it bigger. Okay. So where did Nastran go? I got rid of it. So now we're going to run Nastran, okay? So I'm going to go to that directory and pick that input file. And that's all that's going to happen with Nastran, all right? So I'm going to move that over here. Now what I want you to look at is what goes on in that actual directory when I click on this file, okay? So when I click on this, it's going to say take this input file and solve it in Nastran. So here's the Nastran program itself. Not much going on. We're going to open it or run it. And now, hopefully, you should see files. Oh, No, we got this other one where you can put in some optional keywords, right? But we want to just run it, so I'm going to hit run. It tells you what it's going to solve and where it's going to put the output, okay? So we hit run. And now you can see it's adding files to the directory. Put some scratch files, erases some of them, and then put some status files, okay? Well, hopefully it worked. If it did, our output actually should be in this FO6 file. It's just a text file, so let's open it up and see what it looks like. And this is sort of the moment of truth, right? Because if I did this wrong, we'll get an error here. So this is an FO6 file. You can read it, although they didn't do a great job making it very readable. It starts off with a bunch of ads. You don't worry about that too much. And then basically it sort of summarizes your input file. So here it has like the header. It talks, now it sees here's the solver, and here's the load cases, and here's the bulk data, and all that sort of stuff. Okay? And it looked like it solved it. Okay? So here I have reaction forces, okay, on okay, let's be careful about this. Oh, this is the solving the system. It's checking for equilibrium here. Where are the results? Second load case, equilibrium. Okay, so here are the results, okay? So here are our nodal displacements, all right? For load case 1, you can't see it here because my face is in the way. It says subcase 1, and here for subcase 2, right? So this is the displacements for the first subcase when both nodes are fixed at grid points 1, 2, 3, and 4. Here's the translation of the x, y, and z, and the rotation of the x, y, and z. You can see everything is 0 except for the translations in the x direction at node 3 and 4, because those are the constrained ones. And, you know, if you go back to the video where we solved this problem by hand, you can see these are the exact results we got. Now, if you go to the second load case, they change. You can see we have the displacement of 0.2 at node 2, and the displacements have changed a little bit, but it gives you the displacements, the x for that one, and I think those are the same we got before as well. Here are reaction forces at nodes 1 and 2. Again, forces in the x, y, and z direction, and moments, you know, work conjugate with the rotations. Again, only forces are going to be in the x direction. Here it is for the second load case, the reaction forces for the second load case. Here are the forces in the springs for the first and second load case. Here's for spring 1, spring 2, spring 3. That's all there are. Second load case. And then the strains and the stresses and all that sort of stuff, okay? So those are your results. All right, that's pretty much it. You may get errors, and if you do and it doesn't run, those errors will very often be in the FO6 file. Sometimes they'll actually be in the FO4 file or in the log files. All those you can read with a text editor like Notepad++, and it should work. All right, you can actually also look at the fancy displacements with the XDB file. So that's why I put that line in here somewhere with the param. Like I said, you didn't have to put this param post 0, but if you do, it will write out this XDB file, which is kind of nice because I can then use a graphic post processor like HyperView here and read in those XDB files. So we're going to read in the files. Open model, I think. And is it a model? No, I got to do results. Where do we do this again? Probably should have done this in a different video. Because this is HyperMesh. I need to do HyperView. Excuse me. All right, well, you can turn this video off now if you want to, but let me see if I can find HyperView. HyperView. HyperView will allow me to receive the XDB file, so that's kind of cool. We'll wait for it to load. My computer's slow. It usually doesn't take this long. All right, here it is. Here it is. It looks something like this, okay? And it's a little jumpy on my computer for some reason. That's good enough for now. So here's where we load the model and the results. They're all going to be that XDB file. So I'm going to go into desktop. Here's where all my results were. Where were they? Spring. There it is. You can use the .bdf as the model or the XDB file. It doesn't really matter. But for the results, you definitely want to use the XDB file. So you can see here, it's going to use spring.bdf as the input model, and then the results are in spring XDB. And then when I hit apply, yeah, it's kind of boring here, but because it's spring elements. But there are our spring elements. That is it. Deformed for like the first like subcase, right? So we could actually like look at the element forces if you want to, right? No. Here's this one. See last forces, this will do it. There you are. So here's the first spring, second spring, the third spring. I know it looks a little weird, but that's because node 3 is all at the same point. And this shows you the forces in the spring elements, okay? So for more complicated models, it's actually very useful to look at them graphically. So that's what's good about the XDB file, okay? All right, well, that was a lot of stuff, and I really went a lot farther than I wanted to, but that's it. You can stop it and go through it a little more slowly to go over the things I missed. Don't worry, we will cover what a lot of those fields mean later on in the class, but this is just to get you started to do some spring elements problems. So you can probably take that template and modify it relatively easy to solve a variety of problems in Chapter 2 of the Logan text, okay? All right, good luck.